Let us consider the case of a full wave rectifier connected to a R load through an L filter. Bridge rectifier is considered here because the waveforms of output voltage and input current will be identical as explained already. So as long as the output current IL, the current through inductor, is positive, D1, D3 are in common cathode connection, so one of them should conduct, and D2, D4 are in common anode connection and one of them should also conduct as long as the output current IL is positive. And how do we know which diode conducts in which interval? By looking at the voltage at the other nodes. In the case of common cathode connection of D1, D3, we look at the voltage across A and B. When VAB is positive, D1 conducts, and when VAB is negative, D3 conducts. Similarly, from the bottom group, when VAB is positive, D2 conducts, and when VAB is negative, D4 conducts. So the current flows from source to D1 to load and back to the source through D2 as shown here in the positive half cycle, and in the negative half cycle the current flows through D3 and D4 as shown earlier. And how does the current vary? If you want to know the variation of current, we need to look at VO dash, because that is what is driving the current in this RL circuit. VO dash is driving the current in the RL circuit. VO dash is equal to VAB when D1 and D2 are on. That is, in the positive half we have this kind of voltage appearing across this RL circuit. So the solution of differential equation Vm is equal to Ri plus LdI by dt will give us the variation of current, and that will be a sinusoidal plus exponential as explained earlier. So if we start with an initial condition, so for example this is the initial condition, it will follow a sinusoidal plus exponential which can be plotted like this. And what if we start with zero initial condition? That can be shown by this simulation result. This result is obtained in Plex. So to start with, if you start with zero initial condition, the current will start rising, and now the current will reach one particular point in the positive half cycle. At the end of positive half cycle, the current will be here. Then what will happen? Since the diodes D3 and D4 start conducting now, why? D3 will come into picture because the inductor current is still positive and the VAB voltage has gone negative, so the current flow has to be there, and for that condition of positive current flow and VAB being negative, we know that in the common cathode connection D3 should conduct as soon as VAB becomes negative. Similarly, D4 should take over current from D2 as soon as VAB becomes negative. Why? Because now A is the most negative terminal, A is more negative than B in the negative half cycle. So in the common anode connection of D2 and D4, D4 is the one which conducts because the current entering the common anode point is again positive. So when both D3 and D4 conduct in the negative half cycle, what is the voltage across VO dash? What is the voltage VO dash? VO dash is again, now it is VBA. VBA, that is the negative of input voltage. So we have the same waveform that is appearing across this RL circuit in the positive half as well as negative half as shown here. So in the case of positive half, it is VAB, directly the source voltage, and in the case of negative half, it is VBA, it is the flipped version of input voltage. Since the input voltage itself is negative, we will have the same positive voltage that gets applied across LR. How does the current vary now? So the current will vary again as sinusoidal plus exponential function from this point, because we stopped at this point, that is the end of positive half cycle. So the current will start following another sinusoidal plus exponential and reach another point at the end of negative half cycle. In the positive half cycle, again the same waveform appears, same source voltage waveform appears, sinusoidal voltage appears across RL, positive of that. So it will follow a sine plus exponential like this. And when will steady state be reached? When this point, the current at this point becomes equal to the current at this point. So the periodicity here is twice the periodicity of input voltage. So what we represent in the slides is waveforms under periodic steady state. How is it different from the case of a half-wave rectifier? In the case of half-wave rectifier, we had an exponential fall interval. We had an exponential fall interval in the negative half. Why? Because in the negative half, diode D2 was conducting and the RL circuit is simply shorted at the input. So VO dash is 0. That is why we have this exponential fall interval. Whereas here, we don't have that exponential fall interval because we have the negative of input voltage. The flipped version of input voltage is getting applied across LR, and it will have a similar variation as that in the positive half, and it will continue. And what is the average output voltage? The average output voltage, the average value of VO dash is same as the average value of VO average, and that is equal to 2 Vm by pi, which can be obtained by integration. This again is because of the fact that the average voltage across inductor is 0 in periodic steady state. And how about the source current? Source current Is is equal to the inductor current in the positive half, whereas Is is equal to negative of inductor current in the negative half. So the source current will have both positive and negative values. So here is the source current in the positive half cycle. So it will have positive portion and also negative portion, and the average value of source current is 0. So we are drawing an AC current from an AC voltage source. However, the current drawn is not sinusoidal, but we were not even drawing an AC current in the case of a half-wave rectifier. The source current had a finite average value as seen from these waveforms.